Welcome back to module 4, where we are trying to find out the connection between the linear algebra and quantum mechanics. And under grid representation, we have understood how to represent a wave function, and then we are trying to represent the operator. And in order to represent the operator, we have used a finite difference method to represent the derivative operator. So far we have seen the first derivative, how to represent, but we have to remember that first derivative is not present in the Hamiltonian operator. So, Hamiltonian operator has second derivative, because kinetic energy by 2m, this is the second derivative. So, we have to get the second derivative expression for the with the help of finite difference method. So, for that what we need to do is that we have seen the Taylor series expansion for the forward and backward expressions, and previously we have taken subtraction. Now we will take the addition. So, we will add them together. So, if we add them together, we get x naught plus delta x plus f x naught minus delta x equals 2 f x naught plus 2 second derivative at x naught divided by 2 factorial delta x square plus 2 plus 2 fourth derivative, which is taken at x naught divided by factorial 4 delta x to the power 4, like this. So, we get this expression adding forward and backward difference expressions, and then we will rearrange this equation a bit to find out this second derivative. So, second derivative is going to be then dx2, second derivative at x equals x naught is going to be then f x naught plus delta x minus 2 f x naught plus f x naught minus delta x divided by delta x square, plus the remaining part is going to be this one, and because it depends on x to the power 4, but I have to divide x to the power 4 delta x to the power 4 by delta x to the power x square. So, that is why finally the error is going to be delta x square. That is going to be the error. So, this expression represents the central difference expression for second derivative at point x naught, and this exhibits an error which is delta x square. Quadratically it will scale with delta x square delta x, and so based on this one can now construct what will happen for different points. So, we can write down that I can have this y1 double dash, that is the second derivative at y1 point. So, I started with my wave function was something like this, y0, y1, y2, y3 like this, and I am trying to find out the derivative at each point. And if I want to find out the derivative at each point, how do I get that? I can get this by delta x square. Then in order to find out the derivative at y1 point, I need to know the derivative one step forward, which is y2. Sorry, I need to know the function value one step forward, that is y2. Then function value at that point 2 multiplied by y1 plus function value one step backward, which is going to be y naught. So, this is the expression for the derivative at y1 point. Similarly, derivative at y2 point is going to be 1 by delta x square, then function value one step forward, which is y3, minus function value at that point y2 plus function value one step backward, which is going to be 1. And this is the way we can go ahead. Finally, I can have y n minus 2 position where I have, because here we have n minus 1, total number is n number of points we have is starting with 0, that is why it is ending at n minus 1 if I have total n number of points, and that is why I will not be able to get the derivative at this point because I do not have any point one step backward. Similarly, I cannot get the derivative, second derivative, particularly second derivatives with central reference method. I cannot get the derivative at this point also because I do not have any points one step forward, because I need one step forward and one step backward values also for the function. So, I have started with y1 and I will end with yn minus 2, where I will be able to write down delta x square, then y, then once function value one step forward, which is n minus 1, minus function value at that point n minus 2 plus function value one step backward, which is n minus 3. That is the way we will get this. Now, this set of expressions, set of equations can be very easily represented with the help of matrix representation. And how we know matrix multiplication very nicely, and we will use that matrix multiplication method to represent this this set of equations. So, we have this f, the wave function, which is represented on the x grid already, and we have this x grid representation. So, I will write down the x grid representation as like this. So, I have the wave function as y naught, y1, y2 like this, y n minus 1. This is my wave function. On this wave function, this operator is acting, and if this operator can be represented as 1 minus 2 1 0 0 0, then 0 1 minus 2 1 0 0, then 0 0 1 minus 2 1 0 like this, and we can continue this, and finally I will have here 1 minus 2 1 like this. So, what we see here, and then I have this 1 by delta x square, this is represented by the function after taking the derivative, discretized function after taking the derivative. So, I get y1, I get y2, I get y3 and like this, and then I get yn minus 2 also like this. And why this is the way it is? Because if we multiply this operator by this matrix by this matrix, then what will happen? I will end up with y1 double dash. I have to equate the left hand side element to the right hand side element. So, in that case I will be equating this y1 value to the first product. So, that product is going to be y naught minus 2y1 plus y2 plus all our others are 0 because it is multiplied by 0. So, in the end I get back this expression. Of course, we have this 1 by delta x square. So, each element will be equating each element and will get back this set of equations. So, this entire set of equations one can represent in this matrix form. The moment I represent it in the matrix form, what I get immediately is the vectorial matrix representation of the derivative operator, because I started with, so basically this d, if I use d d2 dx2, this operator can be expressed in the matrix form in the under grid representation as this 1 0 0 0, then 0 1 minus 2 1 0 0 0 0 1 minus 2 1 0, like this, and we will continue this, and finally we have this 1 minus 2 1 0, like this. So, what we get, this matrix is actually the dimension of this matrix is going to be n minus 2 by n, that is the dimension. So, I have n minus 2 number of rows and n number of column. So, I have n number of column and n minus 2 number of rows I have in this matrix, and that is the representation. So, matrix representation of this derivative operator under this grid representation is given by this. So, that is the way we can represent the second derivative in the matrix form. So, we will have one example, simple example, and this example will be helping us because we are dealing with too many numbers. So, we will just reduce the dimension of the system. We have, let us say, the grid is following. I have this x naught, then I have this x1, then I have this x2, and then I have this x3, and finally I have x4. So, this is the grid I have selected, a very small grid I have selected, and obviously the difference between each adjacent grid points is delta x. Now, if we take this and under this grid, if I have the wave function, the function represented by y0, y1, y2, y3 and y4. It is represented, so it is a 5 by 1 matrix. If that is the way the function is represented, then question is, how do I represent the derivative at each point? So, derivative can be represented by, according to the previous discussion, is going to be, I will get only the derivative at 3 different points, y2 and y3, only 3 different points I will get that derivative. At the first point and at the last point I will not get the second derivative, because I do not have the data point which is required to calculate that derivative. So, this is going to be delta x square, and now I will explicitly write down the full matrix 1 minus 2 1 0 0, then 0 1 minus 2 1 0, then 0 0 1 minus 2 1. So, this is the matrix I have, derivative matrix, and then the function is going to be 0 y0 y1 y2 y3 y4. That is the function I have. So, this is your 5 by 1 matrix, this is your 3 by 5 matrix, 3 rows I have, and this is also 3 by 1 matrix. So, that is the way we have the values. And if somehow not somehow, for some reason, if we can say that y0 is 0 and y4 is 0, when I am defining the function for the first time, this function, when I am defining the function, if I select a defining condition, if I select a defining condition like this. So, initial value is 0 and final value is 0. Then what we can do, we can eliminate these two values and we can write down another simplified form, which is going to be y2 dash and then y3 double dash is equal to delta x square. Then this is going to be now reduced. This is going to be minus 2 1 0, then 1 minus 2 1, and then 0 1 minus 2. The entire matrix dimension has reduced now because of this initial defining initial condition, and that is very important to realize. So, the moment we do that, if I use this defining condition for the function, where we are saying that the initial point has to be 0 and the final point has to be 0, which means the boundary. So, in the grid points, the boundary values are actually taken to be 0. If we do that, then this matrix, which was previously 3 by 5, is becoming now square matrix, 3 by 3 square matrix. And defining it in a square form is very advantageous. I will show that why I should do that. And the moment I do this square matrix, this becomes a tridiagonal matrix. Tridiagonal matrix, why tridiagonal matrix? Is because I have now diagonal elements here, then upper diagonal elements, and then lower diagonal elements. Only 3 components associated with the diagonal region is having the finite value, otherwise every other points are going to be 0. So, a tridiagonal matrix should look like this. A tridiagonal matrix, in general, a tridiagonal matrix should look like I have this is going to be a square matrix. I will have always diagonal values, I will have lower diagonal values and upper diagonal values. Remaining part is going to be all 0. So, this is called tridiagonal matrix. And I can represent, so basically this d2 dx2 gives me a tridiagonal matrix when I use this boundary condition, this defining condition for the initial wave function. And this kind of tridiagonal matrix can be used to find out the eigenvalue and eigenvector for the operator. So, we will move on and we will now look at the Hamiltonian operator. This is what we wanted to do. Under grid representation, we have used finite difference method, and under grid representation we will represent that. So, one dimensional Hamiltonian, as we know that Hamiltonian operator is going to be minus h car square by 2m d2 dx2 plus v. This is your Hamiltonian operator. Under grid representation, we have already discretized the wave function. So, wave function is represented by this. This is going to be psi 0, psi 1, psi 2, like this, psi n minus 1, This is the grid representation, and these are the values we have, and we are going to use that defining condition. Defining condition is that at the boundary, that is going to be psi 0 is going to be 0 and psi n minus 1 is going to be 0. This is the defining condition we are going to use for the wave function. So, we have to select the grid such a way that in the end here at the beginning of the grid and at the end of the grid, the psi values should take 0. This is something which we have to do so that I can represent the derivative operator in the tridiagonal square matrix form. And question is, I cannot just represent like this way. I have to check whether I am supporting or am I supported by the property of the Hilbert space, because I am dealing with in the end wave function. So, any wave function which is living in the Hilbert space must be square normalizable, and if it is square normalizable at the boundary it has to be 0. So, this is the basic idea. So, in the reduced Hilbert space, when we will be presenting in this finite grid representation, it is quite clear that this initial defining condition is spontaneously supported or naturally supported by the reduced Hilbert space, the property of the reduced Hilbert space. So, you are good to go with this kind of wave function where the initial and the final values is taken to be 0. And if we have taken 0, then this matrix has reduced to this form. This is going to be psi n minus 2. So, this is now n minus 2 by 1 matrix under this representation. Now, we will use the central difference method to calculate the second derivative. So, I have this kinetic energy operator which is h car square by 2m, then I have d2 dx2 which is now I am going to write down as h car square by 2m. Then for this part I get 1 delta x square value, and then I have this matrix. And remember, in this matrix I will not start with 1 minus 2 1 because I have already used this defining condition. So, I will be using directly as minus 2 1 0 0 0 like this, then 1 minus 2 1 0 0 like this, then 0 1 minus 2 1 0 like this, and then this will be continued. Finally, I will have here minus 2 1 0 0 like this. So, I get a square matrix, but it is a tridiagonal matrix. It has diagonal, upper diagonal and lower diagonal finite values. So, all other values are 0. So, I have this n minus 2 by n minus 2 matrix represented by this. So, what I get is that the kinetic part is represented by this matrix under grid representation with the help of this finite difference method. On the other hand, if I look at the potential part, in the Hamiltonian I had kinetic energy part plus potential energy part, and if this potential energy part has to be now expressed, so potential part is going to be how do I get that? Now, potential, we have to have one realization here. Potential is nothing but a multiplication function. So, I have Vx psi x. So, psi has been already represented by grid. Under grid representation, discretized psi has been represented. So, this is, let us say, psi, and Vx, let us say Vx has a form of like this, let us say Vx. So, if I multiply these two functions, multiplication of these two functions, this is scalar multiplication. So, scalar multiplication is nothing but the multiplication of individual element of the respective matrix. So, what we have is that V can be represented diagonally because it is just a scalar multiplication. So, in the end Vx psi x in the matrix form, it should be like V0 psi 0, V1 psi 1, V2 psi 2 like this, and then Vn minus 1 psi n minus 1, because we have taken psi to be 0, psi 0 to be 0. So, this first term and the last term will be gone because of the boundary condition. So, I have now Vn minus 2 multiplied by psi n minus 2. So, this is going to be now n minus 2 multiplied by 1, n minus 2 by 1 matrix, column matrix. Now, this column matrix can be very conveniently represented by following form. We get this column matrix with the help of this V1, V2, then 0, 0, 0, 0, V3 like this, and then this is going to be V n minus 2. So, this is 0, this is 0 like this way. So, what we get, and here we get psi 1, psi 2, psi 3, psi 4, psi n minus 2. So, basically we get back this element by element multiplication to get this scalar multiplication with the help for the potential operator. The potential operator in the end can be represented as a diagonal form. So, the conclusions we have is that potential part, which is only x dependent, we have to remember that we haven't included any time dependency so far, just we have kept the entire derivation very simple, and we have maintained that one dimension so that we can understand the basic idea behind it. And so, potential part is giving me a diagonal matrix, and kinetic part is giving me one tridiagonal matrix. So, these are the two things, and once we get potential part, potential matrix and kinetic part, both part, it is just a matrix addition in the end we have to do to get the TDSE. Because, and matrix addition we know, matrix addition is done by adding individual element, corresponding elements. So, this is something which we should remember, that in the end, that under grid representation with the help of pseudo spectral basis and using finite difference method, one can represent kinetic energy part of the Hamiltonian in tridiagonal matrix and potential part as diagonal matrix. So, we have with this we have come to the end of this module, where we have discussed quantum mechanics, the connection between quantum mechanics and linear algebra. We have shown different linear algebra terminologies, and also we have shown the analytical approach using matrix algebra. How can I represent different operators? So, this is the general form of the wave function under grid representation. Then this is the general form of the kinetic energy part, and this is the general form of the potential energy part under grid representation. So, we will stop here and we will meet again for the next module.